Hey everybody, gonna go ahead and do the homework problems, a couple homework problems from section 8.3. I've already picked a couple that I wanted to do. So I think we'll look at problem 1 first. So let's just jump right in. And I've done some of the prep work on this one. So conducting a hypothesis test comparing population means mu1 and mu2, we determine the null and alternative hypothesis. So the alternative hypothesis has the greater than, less than, or not equal. And of course, always the null hypothesis just has an equal sign. Greater than is a right tail test, less than is a left tail test, not equal, that's a two tail test. Okay, so for the problem, it says first from a first quantitative sample of sizes n1 equals 18, the following quantities were recorded. And then we have a second quantitative sample of size 27 with a list of numbers. And we want to test the claim at 2% significance. So I guess I'll put this up here. Alpha is 0.02. That the samples are drawn from populations where the first population mean is different from the second population mean. So the null hypothesis is always that the means are equal. But our alternative will be that they are different, which means they are not equal. Mu1 is not mu2, and so that's a two-tailed test. Okay. And so with this list of numbers, you're going to need to type these in or paste them into Desmos to get the mean. I just went ahead and put them in Desmos, and I've already done them. So let me pull this over so you can see it. Okay, so there's my X1 sample. That's the first sample and the second sample here. You can see I have a mean already. So for the first sample, the mean, these have 2 places after the decimal, so I'm going to have to carry 3. So I'm going to do 10.753 for the first sample. Standard deviation is 3.836. And on the sample size, it's 18. Okay, and then for the second sample down here, the mean is 8.484. Second standard deviation, 3.577. And that sample size was 27. Okay, we need to check, going back to the problem here. So it says that each population that we're sampling from is normal here. So we could say normal populations, and that's all we need for the check. Okay. And so let's see if we can start answering some of these questions. So for the null hypothesis, we'll say under variables here, go mu1 and then equals mu2. And for the alternative, if you look at our alternative hypothesis, remember we decided that was a two-tailed test. We'll go over here and pick that. Okay. And then for the criteria for normality, require sample sizes greater than 30 or the population we're drawn from is normal. So at some point that'll be asked, I guess. So our first sample mean, again, it wants 3 places, so we're going to go 10.753. Sample standard deviation 3.836. Second sample mean 8.484. Oop. Second standard deviation 3.577. Okay, and the criteria we said we're satisfied because each population is normal. Yeah. And let's check everything here. Yeah, everything's great, so we can go on. Looks like it wants our test statistic next. So I'll go ahead and compute this over here. So our x bar 1, 10.7, I've got the formula here as you can see. Sorry, I didn't mean to do that. So we'll do x bar 1, which is 10.753. Minus x bar 2, which is 8.484. And then minus the mean difference. I'll put a note here. The mean difference will always be 0 for the problems you're getting. And so you just say minus 0 here. Okay. And then we need down below the standard deviations. So 8.484 for the first one. Of course, we're squaring that over n1, which was 18. Okay, that's a mistake. Okay, so the first standard deviation right, so our first standard deviation is 3.836. I'm going to square that and divide by sample size, which is 18. Okay, and then the second standard deviation, 3.577. Also have to square that and divide by 27, the sample size. Alright, so take a moment and try and do that computation here. First the fraction, then the numerator. Okay, the denominator now. Start with the square root, and then a fraction. And now the first standard deviation, 3.836. Gotta square it. Real common for people to forget to square. Obviously that would throw your number off. Now don't leave this. Now again, the cursor here is blinking under the square root symbol. Make sure you don't leave the square root. That's another mistake that people make a lot. Okay, and that one's over 27. I think I'll just take a quick glance at this to make sure everything's good. Okay, everything looks great there. So there's our statistics. So boy, that one, how many places do they want? 2 places after the decimal. So that's going to round. 199 goes up to 200. So I'm going to call that 2.00, which is kind of crazy. But that's what we've got. And let's see if we get that right. I'll go ahead and do my check up here. That's good. All right, now the degrees of freedom is its own little adventure. So we have to compute the V1 and the V2 here before you can do the degrees of freedom. So couple of steps here. I'll just go ahead and put it on the notes. So So we're going to do the V1 first. So that's S1 squared over N1. Okay, so that is 3.836 squared over the N1, which was 18. Okay, I'll do that in a sec. V2 is S2 squared over N2. Okay, so this is 3.577 squared over N2. That will be 27. Okay, and we're going to store these values in X and Y on the calculator. So let's go ahead and start. So the first one, 3.836 squared over N1, which is 18. Okay, and just evaluate that. So it's super messy, and we want to keep all the precision here. So if you click on store and then the variable button above it, that'll store it in a variable called X. Okay. Now we'll do the next one. I'm going to clear that screen, and notice if you type X and press enter, that's your value. Okay, so it's always going to come up anytime you put in an X to a formula. Okay, now for V2, it's 3.577, again squared, and then over the sample size 27. Okay, and once again, so again a messy number. I'm going to store that. This time tap the variable button twice to make a Y. Okay, so the two V1 and V2 values are in X and Y. Okay. I'll go ahead and put down the formula. Oh, I guess I could have gotten those values. So it doesn't really matter, but just for the notes, I'm going to write this down. 0.8175 for V1. And for Y, that's our V2. I'm tapping that button too many times. There's Y. Okay, 0.4739. Just putting it down. Okay. And then the formula for the degrees of freedom is you do the V1 plus V2 squared over V1 squared divided by N1 minus 1 plus V2 squared over N2 minus 1. And then you just need to remember that V1 has X. So right above here I'll say that we pressed store into X. Just a little reminder, V1 is X, V2 is Y. Okay, so when I evaluate this formula, I'll clear to fraction, open parenthesis, and it's just X plus Y. Close parentheses, square over, okay, first fraction, it's V1, which is X, square over N1 minus 1. So if you go back, N1 was 18 up here. So we're going to put a 17 here. Okay, next fraction. Plus. Okay, numerator is V2 squared, which is Y. So tap twice to get the Y. Squared over N2 minus 1. N2 is 27, so down here we'll put a 26. And it's actually combining those two degrees of freedom in a kind of really weird formula. And you get 34.78. we have to round this down. First time we've ever done that. Those are the rules. So we take this to 34. Makes it a little harder rather than easier to reject the null hypothesis by doing that. And unfortunately, if you're trying to prove things, you don't ever want to make it easier than what you say. So we have to make it harder. And so down here, I think we can go ahead and put in little fingers crossed here. This is always a real tricky computation. But it is correct at 34, and if you get it wrong, then it'll give you the degrees of freedom right here. Okay, so no worries there. All right, so it wants the level of significance here. So that, if you look up, it was 0.02, so 0.02, and now we need our critical values, and again, this is with 34 degrees of freedom. So critical values are on table A2. We'll go ahead and slide up to that. Okay, so our alpha is 0.02, and it's a two-tailed test. Degrees of freedom we've worked out were 34. Right, so that critical value should be 2.441. Okay, let me get rid of that and go back down here. I'm sketching a little bell curve. Okay, so it's 2.441, but then just keep in mind it's a two-tailed test. On a t distribution. Okay, and the test statistic is 2, so that is not in the tail. Oops. So right here is our test statistic. Again, it's that was 2.00, and it's not out in a tail. So it's not going to be statistically significant. Okay, so I think I'll go back and answer some questions now. Okay, so for the left tail critical value, negative 2.441. Right tail, 2.441. Okay, the test statistic is not in the tail, so no, the test statistic is not significantly different. I should say just these two sample means here are not significantly different. That's probably the easiest way to interpret that. Okay, and so we're all good with everything, and now we want our p-value. So the test statistic is just 2. This is new here, so unfortunately what I'm doing for the p-value is making you think a little bit harder in this chapter. So my apologies, but let me just diagram what we're up to here. So remember, our test statistic was 2.00, and that should be a little less extreme than the critical value. So right about here, 2.00. Okay, and then we want the area of the tail because we're doing a p-value. All right, but when you look up 2.00, well, I'm not making you look it up now. I'm basically having you use this slider diagram here as your table. It's already set to the correct degrees of freedom, so you just need to move the slider to the correct critical value. So the test statistic was 2. So I'm just going to put this in position. I'm trying to put it in position. Having trouble. there. So this is going to be a little more precise because it's using 2 places after the decimal. And so the area to the left is 0.973. I don't want the area to the left. I want the area to the right. So now I'm unfortunately going to have to do the rule of complements. So let me make a little room here. And I'm going to go 1 minus 0.973. And let's do that on the calculator. And so we get 0.027, which is pretty small. But unfortunately, we have to double this. So just keep in mind, it's a two-tailed test. So the p-value is 2 times 0.027, which is going to be 0.054. Okay, so that's actually going to be, that's actually pretty big. It's bigger than our alpha value. Alpha was 0.02. So with the p-val of 0.05, and then focus a little bit less on the 4, just think about 0.05. This is bigger, oops, greater than or equal to our alpha, which is 0.02. And so when it's not less, we don't reject the null hypothesis. Which means we don't support H1. H1, which had said that the means are not equal. So they're different, but they're not substantially different. They are within margin of error of each other. Let's just finish this thing up. So according to this, the p-value we did was 0.054. So you can see that we're taking the right tail and doubling it to get this. Okay, so let's just double check that. Where to go? So that's the right p-value. And again, we said that we're going to fail to reject. We're not going to reject the null hypothesis, so fail to reject. And then a conclusion I don't think we have to do because this one has no context. So we're all done. Hi everybody. Okay, so we're going to get to question 6 in the 8.3 homework. And here we go. Says an algebra professor taught 2 sections of intermediate algebra, which we will assume are representative of all of her students in the course. In the first section, she had students work through carefully designed activities in groups. In the second section, she taught the same material through traditional lectures. The final exam scores for the work group session were as follows, and then the final exam scores for the traditional section were as follows. So we're going to get these means and standard deviations real quick. So I'll just copy that. I've got it all set up in Desmos just to paste in here. So for the mean, I'll say, so x1 will say with the square bracket, those numbers. And so we have a mean and standard deviation. And then for the other, here's the second sample. And here are the values. Okay, so we've got everything. These have no places after the decimal, and so we're going to do one more than that. So we'll round to 1 place after the decimal. So let me just kind of squish this down. Okay. So I did not get the alpha value, but we'll do that next. So for this first sample, the mean, we're just going to go 77.9. And the standard deviation, there's the mean, here's the standard deviation, we'll go 19.1. And the sample size was 21 in the first sample. Okay, now in the second sample here, the mean was 64.4. Standard deviation down here, we'll say 13.8. And the sample size was 26. Okay, so again, those are a little small, less than 30. So I hope they'll tell us that this is from a normal population. We'll see that in a second. So back to this. Okay, so it says at a 1% significance level. Oh, okay, so alpha is 0.01. Tests claim that the group with the group work section had a higher mean final exam score than the traditional section, and so that's the first sample, and we'll assume the populations of scores are normally distributed. Okay, so we got to get our hypotheses. I've already got a null hypothesis. It's always that the means are equal. But the alternative, it says the first group, mu1, the first group has a higher mean, mu1, than the second group. Okay, so there's our null and alternative hypothesis. We can go ahead and put that in. So you have to click on vars here. So mu1 equals mu2 there. And then same thing here, click on vars. And this one's going to be mu1 greater than mu2, like that. And of course, pointing to the right makes this a right-tailed test. Okay, now the statistics we've already got up above here, and again it's one place after the decimal. So 77.9, standard deviation 19.1, second sample 64.4, standard deviation 13.8, and yes, the criteria is satisfied because the populations are normal, it said, so we're okay there. Okay, now our test statistics. So we'll be referring to the means and standard deviations from each sample plus the sample sizes, which I've got over here. Okay, so let's go ahead and I've got the formula down here for the test statistic. We just put these in. So it's 77.9 minus 64.4, and the hypothetical mean difference is 0, so we'll just ignore that. Minus 0, and then first standard deviation 19.1. We'll square that and divide by n1, which is 21. Second standard deviation 13.8. Going to square that and divide by n2, which is 26. Okay, and now we got to put that into the calculator. So 77.9 minus 64.4, and then over square root with a fraction. All right, 19.1 squared over the sample size of 21. Okay, then plus, don't leave the square root here, plus fraction, where is it? 13.8, square that, over the sample size of 26. There we go. So it's 2.716, and this wants 2 places after the decimal. Okay, 2.72 then. All All right, and that's almost 3 standard deviations of difference between these two groups. So yeah, I think we'll probably call that significant. Now for the V1 and the V2, I'll just remind you that V1 here is the same as this, which is equal to this. Okay, it's the 19.1 squared over the 21. So I think I'm actually going to just copy and paste that. So my V1 down here, my V2 is this one that I'm wiggling right here, so I'll duplicate that and put it down here. Okay, and then just a quick reminder, we're going to do this without any rounding. So do a little clear on the screen. Fraction 19.1 squared over 21. And we'll just hit enter on that and store that in X. Okay, so we clicked the store button and then X here, and we hit enter. It's 17.37. I'll put it down. But again, the full value is much more complicated, and it's been stored in X. Okay, now for the second variance, the V2 value, we'll do this one, 13.8 squared over 26. Okay, so that's going to be that. I'll put in the notes, I'm just going to write 7.32 here. But we have a much more precise value being stored in Y. So you press store again, and then tap the variable button twice to get a Y. And we'll hit enter. So X holds the first variance and Y holds the second variance. So then our next job, let me just slide up on this here. The next job here is to get the degrees of freedom, and V1 is X, V2 is Y. We'll need those sample sizes, so the sample sizes are up above, they're 21 and 26. Okay, so I'm going to put this formula in here, but in terms of X and Y. So first a fraction, then a parenthesis, X plus, tap twice for a Y, close the parentheses, and square it. Denominator, another fraction. Okay, V1 squared, that's X squared over our N1 minus 1. So N1 was 21, so we're going to subtract 1 and divide by 20 here. And then right arrow, plus another fraction. V2, right? V2 squared down here. But V2 is stored in Y, so you tap the variable button twice. Y squared over N2 minus 1. N2 is 26, so we're going to divide by 25. So this will compute the degrees of freedom. It's 35.39 maybe. Let's put it in here in the notes. 35.39. And you have to round this down to a whole number, so we'll just call it 35. Okay, a little bit smaller, but a whole number. Okay, now we can do our critical value. This one is what, a right tail? Yeah, it's a right tail test. So I'll go ahead and mark down my right tail critical value here, but we need to look it up. So again, it's right-tailed, our alpha up above, you can see alpha is 0.01 with 35 degrees of freedom. So let's slide up real quick to our table. We're looking for the critical value. Okay, so again, here, the alpha is 0.01 and it's a one tail this time. Way down to 35 degrees of freedom here. Okay, so I think we can see that it's 2.438. All right, so let me clean this up. And we'll slide on down. Make our note 2.438 is our T critical value. Okay, and then you might note that we got 2.72 up here for the test statistic, so that is bigger than the 2.438, and that's going to make it statistically significant. So I'll just go ahead and plot that just a little bit to the right here, and note that that represents our T test statistic, which we are going to call significant. Okay, and so let's see, we got an answer over here. The test statistic 2.72. We wanted 2 places, I guess. Okay, down here the degrees of freedom, let me check that. Correct, and so the degrees of freedom are 35. Checking that also. Yep. Okay, alpha 0.01. T critical value was 2.438. And we decided that that the test statistic of 2.72 is more extreme than 2.438, so that's significant. Yes, it is significant. Okay. And so everything's great. Now we're using this clever little tool for getting our p-value. Our test statistics 2.72. I'm having you round that to 2 places because that's as precise as I could do with this little graphic we're using here. So again, 2.72 right there. Okay, now we have the area to the left of 0.995. But the area to the right would be the complement, 1 minus 0.995. Which I guess is going to be 0.005. So here down below we're doing 1 minus 0.995. And of course, let me denote the statistic, the test statistic. It was 2.72 on that. And that's our T test statistic. Okay, and so anyway, the p-value 1 minus 0.995 gives a 0.005. Okay, and so our p-value 0.00, obscuring the 5 so that we only look at 2 digits. 0.00 is less than 0.01, which is our alpha. And so whenever it is less, we remember to reject the null hypothesis and support the alternative. H1, I think it said that mu1 is bigger than mu2 up here. Okay, so I'll note that down below. And the mu1 was the average from the group work class. And they did better than the traditional lecture class. So the data support the claim. Actually, I'll just, in words, I'd say the data support the claim that the average final exam score was higher for students in that class. I guess I have to enter a bunch of numbers here. So my p-value 0.005 is what we got. And we are rejecting the null and supporting the alternative. And so we're talking about the alternative in our conclusion. The data do support the claim that the mean final exam score is higher for students in the work group section. Mu1, that's the work group section, and we're saying we support the fact that it's greater than the average in the lecture section. Should be good? Yep, so perfect again, and we are done.